Hello everyone, we're going to talk about section 7.4, which is the basic concepts of probability. So quite a few things we're going to see in this chapter we actually kind of touched on in the last section, section 7.3, but now we're going to see them as official rules and generalizations in a more official ways that your book has written. So first we're going to start with the union rule, which we did mention in one of the examples that we had in our last section. We remember the union rule as the union rule for sets, or as the number of elements in A with union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A and B. So if we divide each term by n of s, or a sample size, or the elements in our sample size, we get the number of elements in our union of A and B divided by our sample size is equal to the number of elements in A divided by our sample size plus the number of elements in B divided by our sample size minus the number of elements in A and B divided by our sample size. So what we see here is that each one of these terms here looks like our property for our basic principle of probability, which we had, which was the number of elements of whatever we're trying to find the probability of divided by our sample size, or the number of elements in our sample size. And since each one of these looks like that, we can replace it with our basic probability principle. So if we do this, we end up getting the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A and B, or A intersect B. This is known as the union rule for probability. So what we did was we took the union rule for sets and we manipulated it to create the union rule for probability. It's essentially the same rule, it's just that now we're doing the probability instead of just the union rule. So the union rule for probability tells us for any events E and F from the sample space S, we have the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F. So we see this in example 5C from section 7.3. So if you'd like to go back, we see that we use this in our fifth example, part C, from our last section, where we touched on this concept. So for example 1, if a single card is drawn from an ordinary deck of cards, we want to find the probability it will be a black card or a non-face card. So what we're going to do is first we're going to start off by saying that we know there are 26 black cards. Since we know that a full deck of cards is 52 cards, they are separated into 4 suits, each suit's having 13 cards each, and we know there's 2 black suits, so we know that there's 26 black cards, or half the deck. So we know there's 26 black cards, and if we're thinking about non-face cards, we know that there's going to be 3 face cards in every suit. We know it's the jack, the queen, and the king. And we're going to count our ace as a non-face card, which it is a non-face card, but on occasion there's some confusion there. So the non-face cards we considered ace through 10, and our face cards are the jack, queen, and king. So we know there's 3 face cards for every suit, and there's 4 suits, which means that there are 12 face cards in a deck. So we know that there's 26 black cards and 40 non-face cards. And this is also thought of as ace through 10, or 1 through 10, for 4 suits. So 10 cards per suit, 4 suits, 40 non-face cards. So we know there's 40 non-face cards, 26 black cards. So since we know of the 26 black cards, we know that that's 2 suits of 13, 2 different black suits, And each one of these suits is going to have 3 face cards. So that means there's going to be 6 face cards in the entirety of 26 black cards. So even though we found that there's 26 black cards and 40 non-face cards, we know 20 of the non-face cards are also black cards. So we know that they share 20 cards in common, is essentially what we're saying. So we're trying to find the probability of a black card and a non-face card. Let's call it N. So we're going to say B is equal to a black card and N is a non-face card. And we're going to use our union rule to find our value here. So let's start off. We know that the probability of B intersect N, or the probability of having a black card that is also a non-face card, since we know there's 20 of them, is going to be 20 divided by 52. Now we could definitely simplify this number, but we're going to have a few other numbers that are going to be divided by 52, so we're just going to leave our fraction as this for right now. So we know that there are 20 cards that are both black cards and non-face cards. Now I want to find the probability of a black card is going to be 26 divided by 52. And the probability of a non-face card is 40 divided by 52. So now we know that we have all the values that we need to solve for our probability of our black cards union non-face cards. And we know this equation is the probability of B union N is equal to the probability of B plus the probability of N minus the probability of B intersect N. So we know this equation, so let's plug everything in. So we know the probability of B union N is equal to the probability of B, which is 26 divided by 52, plus the probability of N, which is 40 divided by 52, minus the probability of B intersect N, which we know is 20 divided by 52. So when we calculate these values, this is going to give us the probability of B union N is equal to 66 minus 20 divided by 52. Come on. There we go. And this is going to be equal to 46 divided by 52. Now we can simplify this a little further. This is the same thing as saying 23 out of 26. So we see that either pulling a black card or a non-face card is actually a majority of our deck. All right, so a lot of these problems takes a lot of kind of background information because we were able to find these values because we know how many cards are in the deck, how many are black cards, how many are non-face cards, how many would be both. And so we know all of these things. And so it was easier for us to create this problem. But a lot of these problems that we're going to see will require certain information that you may have to draw from reasoning or just background knowledge. Okay, so doing example 2 now. We want to suppose that 2 fair dice are rolled. Remember that fair dice just means that they roll evenly, every outcome is equally likely. So we roll 2 fair dice. We want to find the probability that the sum is 8, or both dice show the same number. So what we're going to do here, is we are going to include an image. So give me just one moment. All right, so this question is a little helpful with this image that we have here, taken from the book. For the purpose of this problem, ignore the parts that are highlighted. We're going to highlight new parts that are going to help us. So by using this image, we want to find the probability that the sum is 8, where both dice show the same number. So what we're going to do here is we're going to use pink and actually let's use different colors since they used the same one. So let's do green and yellow. And green is going to be sum is 8, and yellow is going to be dice that show the same number, or we'll call those doubles. So doubles. So we can use our picture here, and if we want to find doubles, or let's start with the sum is 8. So we want to find the values where the sum is equal to 8. So we can look at our chart here and kind of find where that is. So we see diagonally we have up and down, so it looks like our first row is going to be starting with the die is equal to 1, or our first die is equal to 1, and then we calculate every other die, how much that would be equal to. Our second row will be starting with the die that's equal to, and then we find every value after that, and it goes down. So we see in all, there are 36 options, or 36 outcomes. But we want to find when the probability the sum is equal to 8, where both dice show the same numbers, or we have doubles. So if we're starting with the probability that the sum is 8, we need to find all the values in this chart that would equal 8. And we see there's lots of numbers here where we have one number dash another number. That dash doesn't mean subtract. That dash just means that the first die was a value and then the second die was another value. So if we look at this chart, and we can think of all the ways that dice can equal to 8. So we don't necessarily need this chart because we can come up with them, but this chart is helpful for our question. So if we're looking at our chart here, and if maybe we think of something, we think, okay, well, a 2 and a 6 would be equal to an 8. So we can find that value on our chart. Then we can think of another one, and we think, oh, okay, maybe 3 and 5. Okay, well, that's another number on our chart. And also we have 4 and 4, and 5 and 3, and 6 and 2. So we see we have our values here. And we see that's 5 different options, because we can count them 1, 2, 3, 4, and 5. Now we want to think about doubles. So we want to think about all the values that will be the same number. So 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. Easy enough. So we can highlight those values. And what we see that happens here is that we also create another line of values. And it looks like the highlighting tool, yellow does not beat out green in the slightest. So let's highlight that. No, okay. Let's redo this one. Oh no, okay. We're gonna make 4 and 4 be both. We have this value, oh, it's gonna make it green anyway. And these values. All right, so now since we've highlighted on our chart here, we see there's going to be 6 options for doubles and 8 options for the sum is equal to 5 and they share 1. So this means that when we write out, and we'll just say the probability of 8, because we know what that means, or we're going to be writing D as doubles, so let's stick with the letters. So we'll say, we'll write this over here, we'll say let D equal doubles, and E equal 8. All right, so we have the probability that the sum is equal to 8, or E. So we have the probability of E. And we have 36 options, or 36 total outcomes, and 5 of these outcomes will give us a sum of 8. So we'd say that it's going to be 5 divided by 36. Then we want to find the probability of having doubles, which we know that's 6 options out of 36. Similarly to our last problem, we're going to be adding and subtracting, so we're just going to keep them in their basic fractions as of right now. Then we have our one value that they share, or they both contain. So this is our intersection of E and D. And they just share that one value. It's just going to be that 4, 4, that's equal to 8, and its doubles. So we say that the probability of E intersect D is 1 out of 36. Now we want to use our union rule to calculate our probability of finding a sum that is 8, or both dies show the same number. And we know our probability of E union D is equal to the probability of E plus the probability of D minus the probability of E intersect D. So let's plug everything in because we have all of these values. So we have the probability of E, which we know is 5 divided by 36, plus our probability of D, which is 6 over 36, minus our probability of E intersect D, or the element that they both contain. So minus 1 over 36. We know 5 plus 6 is going to be 11, minus 1. We're going to get 10 divided by 36. Or we can simplify this down. That's the same thing, saying 5 over 18. So we know the probability of rolling 2 fair dice and getting the sum of 8 or dice that show the same number is going to be 5 out of 18. All right. Come on. So a word of caution. You may wonder why we did not use the set of 2 through 12 as the sample space in example 1. Remember, we prefer to use a sample space with equally likely outcomes. So the outcomes in set S above are not equally likely. A sum of 2 can occur in just one way, and the sum of 3 in 2 ways, the sum of 4 in 3 ways, and so on and so forth, as shown in the figure 18 that we found. So we couldn't use the sample space of 2 through 12. Our sample space had to be 2 through 36, or 1 through 36. So if events E and F are mutually exclusive, then intersect, oh my god, I don't know why that was so hard. E intersect F is equal to the empty set by definition. Hence, the probability of E intersect F is just equal to 0. So in this case, the probability of E union F is equal to the probability of E plus the probability of F. So that was the same thing we had when we were finding our number of elements, or we were using our union rule to find number of elements, when we were also doing this with disjoint or mutually exclusive sets. So now we can do the same thing. It's the exact same rule that we could use before, and now we're doing the same thing, it's just now we're doing probability instead of number of elements. So another word of caution is that the rule that P union F, or the probability of E union F, is equal to the probability of E plus the probability of F is valid only when E and F are mutually exclusive. When E and F are not mutually exclusive, we use the normal rule, which was the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F. So it's the exact same things before, just now we're doing probability instead of just number of elements. All right, so now we have the complement rule. So If it has not been completely clear yet, what we're doing a lot in this section is we're going through all the old rules that we learned back in section 7.1, and we're just kind of rewriting them and manipulating them so that they are now probabilities instead of number of elements and sets. So now we're working with the complement rule. So we have by definition of E complement for any event E from a sample space S, we get that E union E prime or E complement is equal to S, and E intersect E complement is equal to the empty set. This shows that E and E prime are mutually exclusive, so the probability of E union E prime is equal to the probability of E plus the probability of E prime. But since E union E prime is equal to S, we get that the probability of E union E prime is equal to probability of E plus the probability of E prime is equal to 1. Okay, so that was a lot of letters that were just said. But basically, this is saying that E and E prime are mutually exclusive events. So when we take the union, they're equal to the sample size, and when we take the intersection, they're equal to the empty set. This is the same thing as like saying probability of 0 and probability of 1. So if we want to find the probability of the union between E and E prime, we know that's the sample size, and if our events, or the probability of our events, is the exact same as our sample size, we know our probability has to be equal to 1, or 100%. Same thing goes for E intersect E prime. If that's the empty set, that essentially means it has the probability of 0. All right, so rearranging this, we get this new rule. We now have the complement rule, which we can use for probabilities, and we get that the probability of E is equal to 1 minus the probability of E complement, and the probability of E complement is equal to 1 minus the probability of E. And we get this equation from essentially right here. So that's pretty much where we got this equation, because we're using that probability of E plus the probability of E prime is equal to 1. And now we've just reworked it so that if we need one or the other, we know how to find them. All right, so that was a lot of confusing kind of things, lots of the same letters with just different things. So I don't blame you if you are a little confused, but let's try out an example and see how we do. So for example 3, this is also going to be your turn, number 3. And what we get here is if 2 fair dice are rolled, we want to find the probability the sum is less than 11. So in order to calculate this, we want to find the probability that the sum is equal to, and now we want to think of all the sums that are going to be less than 11. Yeah, less than 11. So starting with our smallest sum, if we have a 1 and a 1, we know it's going to be 2. So we have 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if we want to find the probability that the sum is equal to any one of these numbers, we find the probability of each one So we find the probability of each outcome, and we can add them together. And I'm sure finding the probability of the sum being 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 and 10 would just be so much fun, and you get so much practice. But that's a lot of work. We don't really want to put in that much work. So this would be a lot of work. So let's use our complement rule. We know our complement rule allows us to find the probability of E if we set this equal to 1 minus the probability of E prime, or the probability of E prime is equal to 1 minus probability of E. So what we can do instead easier to find, I'm going to write prob instead of probability. Just know in the future if I write prob, that means probability. So it's easier to find the probability of the complement or that the sum is equal to 11 or 12. It's not right, or let's say. No. There you go. Which is that the sum is equal to 11 or 12. So that would be the complement in this case. So what we're going to calculate now is we're going to find the probability that the sum is greater than or equal to 11. And since we know if we're rolling 2 dice, the highest value we can get is 12, since 2 6s would be our maximum. So if we want to find this, we know that it's equal to the probability of the sum equaling 11 plus the probability of the sum equaling 12. So if we want to find this, remember we have to think of the combinations that would give us each of these values. So we have sum greater than or equal to 11. So if we want to find the probability of the sum is equal to 11, we have to think of the different combinations that when added together would equal 11. Now there's not a whole lot of them, because really the only combinations that we can have are 5 and 6. But we know that there's 2 combinations because since we're rolling 2 dice and the order counts, we know that 5 and 6 and 6 and 5 count. So there's 2 different combinations. So we know that there's essentially 2 out of 36 chances of rolling an 11. Then we have the probability that the sum is equal to 12. Well, there's only one case of that, 6 and 6. So we know there's only one case, so we know it's going to be 1 out of 36. And when we add these up, this just gives us 3 out of 36, or 1 out of 12. And now we can use the complement. So we can say, now we can use the complement rule. So what we're going to get in order to get that, a probability of the sum being less than 11 is equal to 1 minus the probability of the sum being greater than or equal to 11. So this is the same thing. And we already know the probability of the sum being greater than or equal to 11, 1 over 12. So when we say the probability of our sum being less than 11, we know that's equal to 1 minus 1 over 12. We know that 1 is technically 12 over 12. So when we calculate this value, we're going to get 11 over 12. So we know now that the probability that the sum is less than 11 is equal to 11 over 12. So even though this question seems very simple, there was a lot of thought process that had to go into it, because we know that there's a way that we could do this, but it would take a long time and it would take a lot of extra work that we don't necessarily have to do. Or we can use this rule and find our complement and then calculate our value that way. All right, so now we're going to get into odds. So sometimes probabilities are given in terms of odds, a comparison between the probability of E and the probability of E complement. So an example, suppose that the probability of E is 4 over 5. Then the probability of E complement is 1 over 5, because we know that we can get the value of the probability of E complement if we just take 1 minus the probability of E. So we know that 4 over 5 is going to be the probability of E, and the probability of E complement is 1 over 5. This means that we predict E will occur 4 times out of 5, and E prime will occur 1 out of 5 times. So we see that each one, we see 4 out of 5 times and 1 out of 5 times. Now when we write this in terms of odds, what we'll do is we'll say that the odds are in favor of E are 4 to 1. So we just take the numerators, and whenever we say odds, we say our odds are in favor or our odds are against. So in this case, since E, or the probability of E, is 4 out of 5 times, and our probability of E prime is 1 out of 5 times, we're going to say that the odds are going to favor E, because it is going to happen 4 times out of 5 in comparison to E prime, which is 1 out of 5. But when we write this, we say that the odds are in favor of E are 4 to 1. So we just take the numerator. The whole 5 times is kind of just dropped when we write our final answer. We say the odds are in favor of E are 4 to 1. So, as your book calls it, we say the odds in favor of an event E are defined as the ratio of the probability of E to the probability of E prime, or the probability of E divided by the probability of E prime, where the probability of E prime is not equal to 0. Because obviously if it's equal to 0, we're going to divide by 0, and that's not a real number. So we also see that in this case, that was too blue. In this case, if we had the probability of E divided by the probability of E prime, and we know that the probability of E was 4 over 5, and then we're going to divide that by 1 over 5. We know that when we divide by a fraction, that's like saying we multiply by the reciprocal. And we know the 5's cancel out, and we get 4 over 1, which we know that's how we made the comparison. We said 4 to 1. So that's how we get to drop the overall amount of times. All right, so let's try this out. We say that, for example 4, which is also your turn, number 4, if the probability of snow tomorrow is 3 out of 10, find the odds in favor of snow tomorrow. So when we want to write this out, we're going to let S equal snow tomorrow, and we're going to let S complement be no snow tomorrow. So we're going to use our complement rule, because we know what the probability of snow tomorrow is, but we don't know the probability of no snow tomorrow. So use complement rule. to get probability of snow prime, or S prime, is equal to 1 minus the probability of S. We know that S is 3 over 10, so we're getting 1 minus 3 over 10. 1 is like saying 10 over 10, so 10 minus 3 is going to be 7 over 10. So our probability of no snow tomorrow is 7 over 10. Now we know our values of our probability of snow and our probability of no snow. And remember, we want to write this in odds, so we're going to calculate our probability of snow divided by our probability of no snow. So when we do this, we're going to say by our definition of odds, we get P of S divided by P of S prime. And we know that this is going to be 3 over 10 divided by 7 over 10. So what we can do now is just take our numerators and call it a day, but let's simplify this out first. So we know that when we divide by a fraction, that's like multiplying by its reciprocal. And our 10s cancel, and we're left with 3 over 7. So we're left with our definition here, or our value of 3 over 7, and we want to find the odds in favor of snow. So we have 3 over 7. So when we write our final answer, we would say our odds in favor of snow tomorrow is 3 to 7. So whenever we write odds in favor of, the number that we found of the probability that we're thinking of that it's in favor of always goes first. So even though 3 is obviously less than 7, we would still say our odds in favor of snow tomorrow is 3 to 7, because we know that the probability of snow is 3 over 10, probability of no snow is 7 over 10. So we write it in favor of 3 to 7. If we wanted to rewrite it as our odds against snow tomorrow, that would be written as 7 to 3, because we're thinking against our probability of snow. Then if we think in other terms, we can rewrite this a lot of different ways. But it's important to know that when we think of in favor, the probability of something happening comes first. If we're thinking against, then whatever we're trying to find comes second. Okay, so we can generalize the following from example 4. If the odds favoring event E are m to n, then the probability of event E is equal to m divided by m plus n, and the probability of E prime is equal to n divided by m plus n. So this is kind of how we would find our overall number of times that we did something, or our overall number of events. So trying to think of it this way now, for example 5, we have if the odds against a certain horse winning a race are 13 to 5, what is the probability that the horse will win the race? So we can also say that this means the odds of the horse losing the race is 13 to 5. Since we know that the odds against a certain horse winning a race are 13 to 5. So rewriting this, we think that the odds in favor of the horse winning would be 5 to 13, but the odds of the horse losing the race is 13 to 5. So this tells us, or this indicates, that, and let's assign these values. So if we say that the chances of the horse losing was our probability of E complement, this indicates that N is equal to 13 and M is equal to 5. Now we want to use our equations here to write these out. So we know that the odds of losing is 13 to 5. And that is going to be the probability of E complement. So the probability that he loses, so we're going to write probability of lose, is the same thing as saying the probability of E prime, which we say is N divided by M plus N. We did say that was N, right? Yeah. So then we get that that's 13 divided by 13, or 5 plus 13. So we get that the probability of the horse losing is 13 over 18. So this tells us there's 18 outcomes. So now, since we already found this definition, we can use our generalization we found earlier to find the probability of winning. So we find the probability of winning, which we're saying is equal to probability of E, if we're thinking about our generalization. And that's going to be M over M plus N. That's 5 over 5 plus 13, which is 5 over 18. So we found the probability of the horse wins. Now if we're going to write this in terms of odds, remember we have to write it differently. So, we just needed the probability that the horse will win the race. So the probability that the horse will win the race is 5 divided by 18. If we wanted to rewrite our odds, we would say that in favor of the horse winning, the odds will be 5 to 13. In this case, we just wanted the probability. So this would be our finished problem. All right. So on our next part here, we have probability distribution. So a table listing each possible outcome of an experiment and its corresponding probability is called a probability distribution. The assignment of probabilities can be made on an empirical basis or theoretical reasoning, provided it satisfies the following condition. So the things that we've been doing, we know that our empirical basis would be on our past experiences or past data that we have, or just our theoretical reasoning, which would be, things like rolling dice and cards and things like that, because we can think about those things theoretically pretty easily, but as far as empirical basis goes, we know that's hard data that we would have to work with. So the assignment of these probability distributions can be either empirical or theoretical. They just have to satisfy these following conditions. So we have the properties of probability. We say let S be a sample space consisting of n distinct outcomes, S1, S2, all the way to Sn. Then an acceptable probability assignment consists of assigning to each outcome Si a number P sub I, the probability of Si, according to these rules. The probability of each outcome is a number between 0 and 1, which is inclusive, so we say that the probability of 1, or our first probability of outcome 1, has to be between 0 and 1, and every probability has to be between 0 and 1. And then we have number 2, the sum of the probabilities of all possible outcomes is 1. It has to equal 1, not 9.899 or 9.999. Has to equal 1. Can't be more than 1, can't be less than 1, has to be 1. So when looking at these properties, all we need to keep in mind is when we have these tables or these lists of distributions is that each outcome has to be between 0 and 1, and they all add up to be 1. Those are the only things we care about. Okay, for example 6 here, we have an experiment is conducted for which the sample space is S is equal to the set of S1, S2, S3, S4, and S5. Which of the probability assignments in exercises 34 through 40? So this originally was 35 through 40, but we're just going to do 35 through 38 in this case. So we're only technically working with S1. Oh wait, no, each one has different values of S. So we're only working with 4 instead of the original 6. But we say which ones are possible for the experiment. If an assignment is not possible, we say why. So basically when we're looking at this, all we're thinking about is each probability between 0 and 1, and do they all add up to be equal to 1? Only things we care about. And we're just saying if it is possible or not, and then why if it's not. So starting with A, we have our outcomes and we have our probabilities. So we have different probabilities here. Now we need to look at each one to make sure it's between 0 and 1. So looking at S1, we have 0.09. That's between 0 and 1. S2, 0.32. That's between 0 and 1. 0.21, that's between 0 and 1. 0.25, also between 0 and 1. And 0.13, all between 0 and 1. So our first condition is satisfied. Done. Now we just need to make sure that our second condition is satisfied. And that is just making sure that when we add all of these values up, they are equal to 1. So I invite you to take a moment and figure that out and add those up. If you had, you should get that yes. This, so let's go with this probability, I'm gonna write prob, assignment is possible. Yeah. And this is because when we add these up, they're equal to 1, and each one is between 0 and 1. All right. Since 0.09, 9, oh man, plus 0.32 plus 0.21 plus 0.25 plus 0.13 is equal to 1. And they're all between 0 and 1. Okay. So that's the only time I'm going to write it. Now, after this, whenever we say that it's possible, we know that that is the assumption. So now, for B, looking at our table here, we have all of our different outcomes, and we have our probabilities. So we see that S1 is 0.92, between 0 and 1. S2 is 0.03, between 0 and 1. S3 is equal to 0. But we remember that our condition is saying that it is inclusive, so it includes 0. So S3 is okay because it's between 0 and 1, and it includes 0. Then S4 is between 0.02, between 0 and 1, and S3 is S3 is 0.03, between 0 and 1. So our first condition is satisfied. Now our second condition, which we just need to add these values up and see if they equal 1. So if you add them up, you should get that they are equal to 1. So we say that yes, this probability assignment is possible. All right, now for C. We have S1 is equal to 1 divided by 3, S2 is 1 divided by 4, S3 is 1 divided by 6, S4 is 1 divided by 8, and S5 is 1 divided by 10. We see that each one of these values is between 0 and 1. Nothing is less than 0, and nothing is greater than 1. So now we just need to add them up. So we've got 1 divided by 3 plus 1 divided by 4 plus 1 divided by 6 plus 1 divided by 8 plus 1 divided by 10. So I invite you to calculate this value on your own. And if you did, I would highly suggest calculating this in decimal form. But if you had, you would end up getting 0.975. And remember, we said that it has to equal 1. So we say, no, this probability assignment is not possible since the sum is less than 1. Then for our last part, D, we have all of our outcomes. Now we have our probabilities, which are 1 over 5, 1 over 3, 1 over 4, 1 over 5, and 1 over 10. Once again, they're all under, or they're all between 0 and 1. Nothing's less than 0, nothing's greater than 1. Now we just need to check the sum, just like before. So we have 1 over 5 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 10. And if you add those values together, you should end up getting 1.083, which is greater than 1. So we say, no, this probability assignment is not possible since the sum is, more than 1, not less. All right, so using our properties of probability, we were able to answer if each one of these different experiments were possible probability assignments or not based on the 2 conditions that we had to satisfy. So as long as those 2 conditions are satisfied, they are possible, but as soon as one does not satisfy, it is not. All right. Now for our last example, we have example 7, which is also number 53 in your book. And this is about color blindness. So color blindness is an inherited characteristic that is more common in males than in females. If M represents males and C represents red-green color blindness, we use the relative frequencies of the incidences of males and red-green color blindness as probabilities to get that the probability of red-green color blindness is equal to 0.039. The probability of the intersection of M and C, or male and red-green color blindness, is 0.035. And the probability of the union between male and red-green color blindness is 0.491. So we want to find the following probabilities. We have A, which is probability of C complement, B, the probability of M, C, the probability of M complement, and D, the probability of M complement with intersection of C complement. So starting with A, we have a probability of C complement. Now, we have the probability of C, so we can find the probability of C complement. Since we know that we can find the probability of C complement, by subtracting the probability of C from 1. And this is the same thing as saying 1 minus 0.039. This gives us 0.961. So we have the probability of C complement, or basically the probability of not having red-green color blindness, is 0.961. Now we want to find B, which is the probability of M. Now, we don't know the probability of M or M complement, so we can't use the complement rule. But what we can use is the union rule. Let's actually give these labels. So let's say use complement rule. And here we'll use the union rule. And we're just going to do this colon. So if we want to use the union rule, we know that the probability of M union C is equal to the probability of C plus the probability of M minus the probability of M intersect C. So let's plug these values in. We know that the probability of M union C is going to be 0.491, which is equal to the probability of C, which is 0.039, plus the probability of M, which we're trying to find, minus the probability of M intersect C, and that's going to be 0.035. So now we just need to solve for the probability of M. So let's simplify the right side. We get 0.491 is equal to 0.004, because we just subtracted that 0.035 from 0.039. And we have 0.004 plus the probability of M. Now we just want to subtract and solve for M. So we have that the probability of M is equal to 0.487. So we got our probability of M. Now we want our probability of M prime, or a complement of M. And now, since we have our probability of M, it's really easy for us to find the probability of M prime, because we can just use the complement rule. So we'll say, use complement rule. And we get that this is equal to 1 minus the probability of M, or 1 minus 0.487, which is going to end up giving us 0.573. So essentially, this is telling us that the probability of not male, the probability of female, is going to be 0.573. All right, so now we can go on to part D. Let's put this right over here. So for part D, we have the probability of M prime at the intersection of C prime. So essentially, we can rewrite this. This is a rule or a trick that we can use when we have things like this. The probability of M prime intersect with C prime is the same thing as the probability of M union C all prime, or the complement of the probability of M union C. And this is because essentially we can distribute our complement sign. And the complement of the union is the intersection. The complement of M is M prime, and the complement of C is C prime. So we can rewrite this. So we know that this is now not with writing all over it. We know this is now P, or probability of M union C complement. So what we can do here now, since we have something that's a complement, we can use our complement rule. So we use complement rule. And this tells us that the probability of M union C complement is equal to, we know, 1 minus the probability of M union C. And we know what probability of M union C is because it gave it to us in our problem. It's 0.491. So this is 1 minus 0.491. And this is going to give us 0.509. So we get the probability of M union C prime is equal to 0.509. And we know we can just rewrite this as the probability of M prime intersection C prime is equal to 0.509. All right, so that last part there was definitely able to do once we knew that little trick. So that is a trick that you can do if you have a case like that. So it's important to remember that. And that finishes up our section 7.4 for today. So we just saw that we had more kind of like basic concepts of our probability that we learned a lot in our last section as well. All right, and this is the last section of our chapter 7. So remember to study up for your test. And as always, if you have any questions at all, feel free to email me or pop into my office hours or submit an anonymous question in our question form, and I will see you all virtually later.